Hello general chemistry students. This is the second video that I'm putting here on YouTube for you guys, talking about and finishing our discussion on Chapter 19's coverage of chemical thermodynamics. Let's go ahead and finish today's lecture, starting up on the slide where we left off. So this takes us into problem number 19 from our problem set. Using the data from Appendix C of your text, what are the values of delta H, in other words the change in enthalpy, and delta S, the change in entropy, at 298 Kelvin for the following reaction? In order to answer this, I'm of course going to turn to some pre-recorded footage from the DocCam. Question number 19 gives us a reaction of hydrogen gas and fluorine gas in equilibrium with hydrofluoric acid. Then asks us to use values from our appendix to determine what delta H and delta S are. As I look in our appendix, the delta H of formation of each of these components is 0, 0, and negative 268.61 respectively. Remember, of course, that it's very, very important when you're looking at an appendix to keep in mind the states. These have to be at these states in order to have these values. If you look up a delta H of formation for these same components in a solid or liquid state, the values will be different. The units on these values are all in kilojoules per mole. The S values, in contrast, are 130.58, 202.7, and 173.51, and these values are all in joules per mole Kelvin. So in order to find out the total delta H for the reaction, we have to find the delta H of the reactants and subtract from that the overall delta H added for the products. That is going to be equal to 2 times negative 268.61 for our products minus 0, because our reactants are all in their elemental states, thereby having no or 0 value for their enthalpy values. I throw that into my calculator, and as you can probably surmise, I get minus 537.2 kilojoules per mole as being the overall delta H for that reaction. In contrast, the delta S for the reaction is going to be equal to the analogous sum of the S value for the reactant, or for the product, my mistake, and subtracted from it the analogous values for the reactants. That's going to be equal to 2 times 173.51 for our products minus 130.58 plus 202.7. When I throw that into my calculator, the final number that I get is 13.74 joules per mole Kelvin. And now with that practice, I'd like to show problem number 11 from our problem set. The value of delta S naught, in other words the change in entropy for the reaction of diamond and oxygen oxidizing to form carbon monoxide gas, is what? Now I am not going to show you pre-recorded DocCam footage of this problem, but instead I'm going to let you guys attempt to do it completely on your own. At last, I can finally, yay, teach you about something called Gibbs Free Energy. Note, it's not really free. You might remember that we learned back in Chapter 5 that generally speaking, exothermic reactions, those are reactions where the change in enthalpy is negative, are usually thermodynamically favorable, though if they have very, very high activation energies, they might not occur very quickly, which I've depicted in this sort of generic energy diagram shown here. By comparison, endothermic reactions are generally thermodynamically disfavored. And in these two figures we can see an energy diagram for an endothermic reaction. That is a reaction where the energy level of the products is higher than that of the reactants. And an exothermic reaction energy diagram in which the energy level of the products is lower than that of the reactants, with an activation energy hill spreading between both reactants and products in both cases. Sadly, enthalpy change, delta H, doesn't really tell us the full story. For example, if we melt ice at room temperature, it totally happens spontaneously, yet it's an endothermic reaction. Now we know that it's an endothermic reaction because it consumes heat. It doesn't give heat off, which you can tell by touching melting ice. When you touch ice as it's melting, does it feel like it's giving off heat? Of course not. So that means it's endothermic. It's actually sucking heat from your hand to convert solid water into liquid water as it melts. Yet it still occurs spontaneously at room temperature, even though it's endothermic, which indicates that it is a thermodynamically favorable process. So why does it happen then? Well, obviously enthalpy doesn't tell us the full story. In the case of melting ice, the reason that it occurs spontaneously is because of entropy. As we melt ice, entropy, or disorder, increases significantly enough to offset the effects of having a positive delta H. So is there some kind of mathematical term that simultaneously incorporates both enthalpy and entropy? Yes, there is. It's called Gibbs Free Energy, also known as delta G. Mathematically, delta G can be expressed as follows. Delta G equals delta H minus T delta S, where T is the temperature, which has to be in kelvins. Now, delta G incorporates both enthalpy and entropy. Thus, if we know delta G, we can totally predict if a process is energetically favorable and spontaneous. Delta G is the awesomest. Now, one warning, when doing delta G calculations, be sure to watch your units. Now, if we keep in mind that delta G incorporates both entropy and enthalpy, then we can understand the following facts from page 804 of our text. 1. If delta G is negative, that is, delta G is less than 0, then the reaction will be spontaneous as written. 2. If delta G is positive, then the reaction will be non-spontaneous as written. 3. If delta G equals 0, then the reaction is at equilibrium. One more thing I want to tell you is that a reaction whose delta G value is negative or spontaneous is called an exergonic reaction. A reaction whose delta G value is positive or non-spontaneous is called an endergonic reaction. This brings us to question number 20 from our problem set. From the answers that you got in question 19 from our earlier slide, calculate the delta G for the following reaction. Once again, I'm going to address this by showing you guys some pre-recorded footage from our doc cam.
If we look at the next problem in our series, it asks us to use the values that we just barely calculated to determine delta G for the same reaction. You might remember that delta G is equal to delta H minus T delta S. Delta H, of course, as we calculated previously, is in units of kilojoules per mole, while delta S is in units of joules per mole Kelvin. We have to reconcile that by converting our delta H to units of joules per mole. Thus, that is going to be equal to 537,000 joules per mole. That is my delta H value, and I subtract from that temperature, which is going to be 298 Kelvin, multiplied by delta S, which is 13.74 joules per mole Kelvin. You'll notice once again, as I always point out, that my units end up working out beautifully. My kelvins cancel each other out. The final answer that I end up getting is minus 541,095 joules per mole, which can easily be converted, and I won't show you the conversion, into minus 541 kilojoules per mole as our final answer.
And now to question 15. An endothermic reaction with a positive delta S or entropy value can still be what? I'm going to answer this question again by turning to some footage from the doc cam.
One more question that I think might elicit some confusion is question number 15 from our problem set. Once again, I don't want to rewrite the whole question here on the doc cam, but we'll instead zoom in on it and take a look and see what it says. So there is question number 15. Question number 15 says, an endothermic reaction with a positive delta S can still be, and then it gives us a list of things. Now here's the deal. I want you guys to understand that endothermic, and in fact we'll go back here and write this down, endothermic just means that delta H is positive. If you remember from our lecture, delta G equals delta H minus T delta S. Delta G, the Gibbs Free Energy expression, actually tells us the full story of a reaction. if delta G is negative, the reaction will be spontaneous. However, you can actually have a reaction that gives you a negative delta G and still have a positive delta H. There are some reactions that are endothermic. They have positive delta H, but they still occur spontaneously. Why? Because of the delta S component. So if we look at this example or this equation, we can imagine mathematically how that might occur. If I have a negative delta H value, if I have a positive delta H value, that is an endothermic reaction, I could still have a spontaneous process, a negative delta G, if my temperature is high and or my delta S is high and positive. So if I've got a very high positive temperature and a very high positive delta S, it's possible that those two terms combined will still make the overall mathematical value here negative and still result in an overall negative delta G. Does that make sense? So once again, the idea is we can make a process still be spontaneous if we do things that involve increasing the temperature or increasing delta S, even if the reaction is endothermic. With that said, let's zoom back in on our options. Option A says non-spontaneous if the temperature is lowered. Now, based on our reaction equation, does that make sense? If I lower the temperature T, is that going to cause my overall reaction to be less spontaneous, or in other words, potentially non-spontaneous? Well, that mathematically does make sense. If I've got a small number T and I've got a positive H, that could potentially give me a more positive delta G value. So option A is actually true. Now, option B says spontaneous if the temperature is raised. Does that make sense? It does. Once again, if the temperature goes up and up and up, the higher it goes, the more negative this is going to be, and hence it can still overwhelm a positive delta H and give me an overall negative delta G value, therefore making this process spontaneous. Option C says non-spontaneous if the temperature is raised, which of course makes no sense based on the argument we just offered. Hence, the only correct answer is option D, both A and B.
Just like delta S and delta H, delta G can also be calculated by using the following equation, equation 19.14 from our book, where delta G for a reaction equals the sum of the individual G values for our products minus the sum of the individual G values of the reactants. Each of those are multiplied by their respective coefficients. Delta G can also be used to calculate a reaction's equilibrium constant, K, by using the following equation, which is 19.21 from our book. K equals E raised to the minus delta G divided by RT, where T has to be in Kelvin and R equals 8.314 kilojoules per mole Kelvin. This brings us to question 12 from our problem set. Given the thermodynamic data in the table given here, calculate the equilibrium constant at 298 Kelvin for this reaction. As usual, I'm going to turn to some pre-recorded footage from our DocCam to address this question.
In this question, we are given a reaction, and then we're given delta H, that is enthalpy, and entropy values for each of these different components. So I'm going to write delta H of formation for each of the components, and I'm going to write our entropy values for each of the components. For SO2, the delta H is 297. For O2, it's 0. And for SO3, it's minus 395. Our entropy values, in contrast, are 249, 205, and 256. We have to keep in mind that the values on each of these for enthalpy is kilojoules per mole, and for entropy is joules per mole Kelvin. That will become very significant later on. In order to calculate the equilibrium constant, we have to remember this equation. The equilibrium constant is equal to E raised to the minus delta G divided by RT. R is the ideal gas constant. T is the temperature that has to be expressed in kelvins. And that we have. What we don't have is delta G. So we have to come up with a way of figuring out what delta G is. You might remember from our text that delta G has an equation. Delta G is equal to delta H minus T delta S. We have, or I should say we don't have our delta G value for each of these components, but we do have our delta H value for each of these components and our enthalpy values. Thus, if we have the ability to calculate delta H and delta S, then we can go back and calculate what the equilibrium constant is. There may be two different ways to do this problem. One would be to calculate delta H for the entire reaction by taking the sum of the individual delta H values for the products multiplied by their individual coefficients and subtracting the individual analogous values for the reactants. And then we would do the same thing for delta S. What I'm going to do instead is a slightly different approach. I'm going to individually, for each component, calculate their individual delta G values by taking delta G and setting it equal to delta H minus T delta S. For SO2, we've seen that its individual delta H value is 297 kilojoules, which is the same thing as 297,000 joules per mole. We then subtract from that the temperature, which is 298 Kelvin, multiplied by the entropy, which is 249 joules per mole Kelvin. You'll see that the units all cancel each other out nicely, or I guess the kelvins do, and we end up getting a final value for SO2 of minus 371,202 joules per mole. When I do an analogous thing for each of the other components, we can see what we get. Once again, delta G is equal to delta H minus T delta S, which for oxygen is going to be equal to 0 for its delta H value, minus temperature is 298 times its delta S value is 205. I end up getting 61,090, or negative 61,090 joules per mole. When I do the same thing for SO3, delta G equals delta H minus T delta S, I get minus 395,000 joules per mole for my delta H, and I subtract from that the temperature, 298, multiplied by the entropy value, 256 joules per mole Kelvin. I throw that into my calculator, and the final answer that I end up getting for that is negative 471,288 joules per mole. So now we have delta G values for each individual component in this reaction. Let's look back now at the reaction itself. The overall reaction we've been examining is 2SO2 gas plus O2 gas in equilibrium with the product 2SO3 gas. Once again, we now know our delta G values for each component. The delta G value for the SO2 is minus 371,202 kilojoules per mole. Our delta G for our oxygen is minus 61,090 kilojoules per mole. And our delta G value for our SO3 is minus 471,288. And sorry, I meant to say joules per mole for all of those, not kilojoules per mole. The delta G overall for the entire reaction is, of course, going to be equal to the delta G of the products minus the sum of the delta G for the reactants. That is going to be 2 times minus 471,288 minus 2 times minus 371,202 plus negative 61,090. When I throw that into my calculator, the final answer for the overall delta G that I end up getting comes to negative 139.82 joules per mole. So that is once again the overall delta G for the entire reaction. Now we should remember the original goal of this problem was to find the equilibrium constant. You may recall that that is equal to E raised to the minus delta G divided by RT. In this case, we now have a delta G value. So I'm going to raise E to the minus 139 0.082 joules per mole divided by R, which is 8.314 joules per mole Kelvin, multiplied by the temperature, 298 Kelvin. When I throw that into my calculator, the final answer, one thing I hasten to point out is that the units all cancel each other out nicely, leaving me a unitless value for my equilibrium constant, which is what I expect. The final number ends up being 2.39 times 10 to the 24th.
And now to question 18. Using data from Appendix C in our text, what is the equilibrium constant K at 298 Kelvin for this reaction? Once again, I'll answer this by turning to the doc cam.
We are given this reaction, hydrogen and iodine gases in equilibrium with iodic acid, also in a gaseous state. And we are asked to calculate the equilibrium constant K. Now, one thing I hasten to mention is that we have an equation in our book that tells us that K, the equilibrium constant, is equal to E raised to the negative delta G divided by RT. We have to keep in mind that T has to be expressed in Kelvin, and R is the ideal gas constant, which is 8.314 joules per mole Kelvin. In this problem, we're given the temperature as being 298 Kelvin. It asks us then to go into the appendix at the back of our book and obtain Gibbs energy values for each of the components in this reaction. I'm going to once again write the reaction, and I'm going to make a little row here that says the Gibbs energy value for each of these components. For hydrogen gas, that is 0. For I2, it's 19.37 kilojoules per mole. One thing I hasten to point out is that when you look this up, you have to look it up for iodine gas as opposed to iodine solid. Those will give you two different values. For iodic acid, it's 1.30 kilojoules per mole. Thus, in order to answer this question, we have to obtain a value for delta G. Delta G is the big mystery value here. Delta G, similar to our entropy values for a reaction, is equal to the sum of the individual Gibbs free energy values for all of the reactant, or all of the products, my mistake, minus the same values for the reactants, and with each product being multiplied by the coefficient before it, as well as each reactant. For this particular reaction, then, we can see that our products have a 2 in front of them. The coefficient in front of iodic acid is 2. So we're going to take 2 times 1.30, we're going to subtract from it. Each of the coefficients in front of these is 1. 1 times 19.37 plus 1 times 0 for the hydrogen gas. When I throw that into my calculator, the overall delta G that I end up getting is negative 16.77 kilojoules per mole. And one thing I hasten to point out is that we have to convert this to joules per mole in order for our units to match in the equilibrium constant expression. So I can multiply that by 1,000 to get 16,770 joules per mole. With that said, I'll now go back to my equilibrium expression. K equals E raised to the negative delta G divided by RT, which equals E raised to the minus, remember delta G is minus 16,770 joules per mole, divided by R, which is 8.314 joules per mole Kelvin. You can see once again the importance of the units right here, right? The temperature is 298 Kelvin. I think I wrote joules up on top for some reason. That doesn't make sense. The units all cancel each other out. Moles and moles, kelvins and kelvins, and joules and joules. And I end up getting, as I throw this into my calculator, a final answer of 870.
That brings us to the end of our presentation and to the end of Chapter 19's lecture discussion on chemical thermodynamics. I hope it's been as fun for you as it has for me. I want you to have an enjoyable rest of the week, and rest assured that I look forward to seeing you guys next week after I return.